Here's a projectile launcher, a trigger. These two are photo gates. What they do is they register as a ball moves through the photo gate. A little current runs from the top to the bottom, and when the ball cuts that current, it registers on the computer. The program data studios will then analyze that data for us and produce some interesting results. To find the speed of the projectile as it leaves the launcher, we have two photo gates set exactly 10 centimeters apart. The two photo gates give us a time difference between A and B, and assuming very little change in velocity, we can use velocity is equal to distance, 10 centimeters, divided by the time that we get, and that gives us a very good estimate for the velocity of the ball as it leaves the launcher. There are a number of different speeds at which the projectile can be launched. After one click, this is the lowest speed. And the highest speed we can time the entire flight of the ball, first as it goes through the two photo gates, and then landing is recorded on a small little landing pad right here. This little landing pad is touch sensitive. When a ball lands on that, it sets off the timer, and it records on the computer when exactly the ball landed. So here's a demonstration of a launch at low speed. Here's a timing of slow speed. Here's a sample of a timing at medium speed. Here's a timing at high speed. So based on the observations from the computer, and knowing that the distance between the photo gates is exactly 10 centimeters, for the slow projectile, we found that the time to go through the two photo gates was 0.0242 seconds, and therefore if we take 10 centimeters or 0.1 meters, divide it by the time that it took to go that distance, we get a speed of 4.13 meters per second. For the medium time, we found that the projectile moved through the two photo gates in 0.016 seconds, or 16 thousandths of a second. And of course, if we take the same equation, distance over time, 0.1 meters divided by 0.016 seconds, we get a time for the medium speed, speed for the medium projectile to be 6.25. And of course, we did the same thing for the fast projectile. It only took 11 thousandths, or almost 12 thousandths of a second. Dividing 0.1 meters by that time gives us a speed of 8.55 meters per second. Alright, so knowing that the slow speed is 4.13, the medium speed is 6.25, and the fast speed is 8.55, we can make a prediction on both the time, knowing, of course, that the height of the launcher, as we measured it, is 1.25 meters above the ground. Given that, and knowing that the object has been launched horizontally, the initial velocity is 0. Therefore, our d is equal to vit plus 1/2 at squared equation from kinematics. Because vi is 0, the term vit becomes 0. D is equal to 1/2 at squared. We can solve for the time by manipulating the formula. We get 2 times the displacement, which is 2 times the height, divided by gravity. Now both of these could be negative. The negative displacement, negative acceleration, they cancel out. T squared ends up being equal to 0.255 seconds squared. And so the time of flight, the predicted time of flight, is 0.505 seconds. And it doesn't matter whether it's going slow, medium, or fast, the predicted time is still 0.5 seconds. And you see from the data that we showed earlier that the time, in fact, was very, very close to 0.505, within a few hundredths of a second. Just a reminder that the time on the top is the time that it took the projectile to go through the 2 photo gates. The time on the bottom is the time that it took to go from the 2 photo gates to the landing pad. Notice that the times on the top are different, while the times on the bottom are very close to being equal. So if we know that the time of flight is 0.505 seconds, or very close to that, then we can just multiply the horizontal velocity, slow, medium, and fast, by that time, and we should get the predicted distance that the projectile moves horizontally. When we do that for slow speed, distance is equal to speed times time, or velocity times time, 4.13 meters per second horizontally, times the predicted time of flight gives us 2.09 meters. That's where we would have to put the landing pad in order for this to work, and exactly that's where it ended up being put. Here's a launch of a low-speed projectile. We placed the landing pad at 2.09 meters. D is equal to V times T. Faster speed, same time of flight, 3.16. That's exactly where the lander was placed. And here's a launch at medium speed. We've set the landing pad at 3.16 meters. And of course, D is equal to V times T. At a higher speed, 8.55 times 0.505, you get 4.32 meters. That's exactly where we placed, or very close to where we placed the landing pad. So here's a launch of the projectile at high speed. We've set the pad at exactly 4.3 meters. Because the pad's kind of large, it gives us a bit of a buffer, but here we go.